Okay, so it's a great pleasure to have Professor Diptarka with us for the IMSc 60 colloquium. Diptarka is a faculty at IIT Kanpur, and before joining as a faculty member, he did his PhD at Kentucky University, and after that he moved on to University of California at San Diego as a postdoc, and then at Max Planck Institute, Potsdam. And he is a quantum field theorist with interest in string theory. His PhD was on problems in string theory. He also worked on many interesting problems in ADS CFT, and now he is interested in non-equilibrium QFT. So he has done some very interesting recent works, and this is the problem that keeps him busy for quite some time now, and he will tell us about the fascinating world of non-equilibrium quantum field theories.
Thank you. Thank you for the very kind introduction. Thank you for the invitation to present some of my excitement to this audience. So is the pointer visible? Okay. Not visible. Okay. So you can see. So I'll talk about some universal aspects of quenches, which is a setup to take the theory out of equilibrium in quantum theories, and all these words will become clear as we go on. And so at any point, feel free to stop me, ask questions. So it will be good to have more interactions. So the basic question that we want to understand are there any universal signatures that appear out of equilibrium? And out of equilibrium is quite important because it's all around us. So for example, we are in an expanding universe. So if we study field theories in time-dependent geometry, so then essentially there are effects like particle creation which are out of equilibrium effects. And similarly, the heavy ion collisions at the colliders are also some aspects of out of equilibrium. And of course, in labs, in cold atoms, people can generate out of equilibrium setups. Okay, so these are all around us. However, most of the tools that we have in field theory are designed to study equilibrium problems and designed to explore universalities and features in equilibrium. So immediately we are faced with a challenge that we need also tools to attempt to answer some of these questions, which we have to also be careful to pose. Okay, so the questions, the main questions that we will kind of pose will be in the context of quenches. So quenches are some setups where you can tune a system out of equilibrium. So what you do is you have a action which describes the quantum system, and you make so it has some couplings. Let's say G is some coupling in that theory, and you make G a function of time. Okay, so for example, if you put say a minimally coupled scalar field in an expanding universe, then the mass becomes time dependent. So mass is like a coupling, it becomes time dependent. So here it can be some arbitrary coupling, it becomes time dependent, it has some profile with time. And then the evolution of the state is non-trivial. Right? So we don't know exactly where we will end up in, even if we know the initial state. Okay, and the kind of questions which we try to understand are what are the time developments of observables. So now these are so this is written in Schrodinger picture. So this is some correlator in some non-trivial state, or you can think of computing some. If you think in the Heisenberg picture, you can think of some very complicated looking operators calculated in the initial state. Okay, so we want to understand what is the time development of these kind of observables. So these are the kind of observables to consider in out of equilibrium, because even if we know the initial state, we don't know much about the final state. So usually in quantum field theory, we calculate S matrices where we have asymptotically in state and out states, right? And out state also has some overlap with the non-interacting vacuum. So we use that fact to formulate S matrix theory. But here we don't know what is the final state. So we have to consider this kind of in amplitudes for out of equilibrium setup. So these observables, and we have to calculate, we have to develop tools to calculate these quantities. So this is one kind of question that we will be interested in. And the other kind of question is, what is this final state? Finally, can we get some indication of the final state by looking at these observables? With respect to some observables, can we give some simplified description of the final state? So for example, can we describe the final state as a Gibbs ensemble? Okay, at late time, can I just use some thermodynamic quantities to characterize the thermal state, to the final state? So for example, this will be a good description if, so we know that if this is a thermodynamic density matrix, then if I compute any observable with this density matrix, it will get a static value, right? It will not change with time. So whether observables have that feature. Okay, so this is another kind of question that we will ask. Okay, so these are the, so is there any effective simple description? So there may be, it may not just be temperature times the Hamiltonian, there may be some other charges which may appear. Also the system may equilibrate to some other ensemble, not necessarily the Gibbs ensemble, but that's the question. Okay, so given a theory, we drive it out of equilibrium, late time, what happens? This is a numerical experiment done with exact diagonalization. So this is in the transverse field Ising model. So there is both transverse field as well as a longitudinal field to make it non-integrable. And there is some periodic boundary conditions, and it's a small, relatively small site. But here, so we are looking at some time average of some local operator. So observable of this kind. So it's very small to see, sorry, but it's an observable of this kind. And we are looking at a time average because we want to get rid of some erratic fluctuation. And you see what happens as a function of time. There are some fluctuations in the beginning, but slowly they die down, and it approaches some value, constant value. Okay, so it seems, so here of course also one has to be specify the initial state. The initial state, of course, if the initial state was an eigenstate, and if I evolve with this Hamiltonian, then there would be essentially no evolution, right? It will just be a phase. But initial state is not an eigenstate. So you can think of the initial state being prepared by some other Hamiltonian. Okay, and I evolve with this Hamiltonian. So it has some non-trivial evolution, but finally it settles down to some constant value. So the question is, can this constant value be obtained also using some Gibbs ensemble? So that connects to this question, because it seems that it becomes it doesn't change as a function of time.
So
yes.
what is in the x in the y-axis is the operator?
It's a time averaged operator.
What is the x-axis?
Time. So with time, you see the fluctuations are dying down. So can you identify this late time value with some thermal answer? That is the question. Okay, so this is the approach to thermalization. Any more questions?
Just to when you said that we cannot know the site in the final state, that means
Computationally difficult, and for some operators, can you approximate it? That was one of the questions.
What are the quench states in the middle of the spectrum?
Yeah, so this has a finite spectrum, right? There are 2 power 12 states. So if you look at the distribution of the eigenvalues, you choose some of the states which are in the middle of the spectrum, which means the energy is in between the maximum and the minimum. Because those are the states which are closely packed. So you expect good coarse graining to appear for those states. So for other states, you have to wait for a very long time. For ground state, it will keep oscillating. Okay, so all states may not have this kind of behavior. All starting states may not show a thermalizing behavior. So these will be the questions. These will be the kind of questions that we want to explore. Okay. So also critical quenches, you can ask this question. So say you take a theory and then you suddenly tune the coupling to a critical value so that you go to a CFT suddenly after some time. Okay, in that case, you can ask whether some of these universalities emerge, whether you get a kind of a thermal static behavior. So it turns out that in this case, there is a prescription. This was worked out by Calabrese, Riccardi, and others, that you can model this state. For the CFT, this appears as a boundary state, and if you, for example, look at the entanglement entropy, as you do this change in the coupling, as you go to the CFT, you will see that the entanglement entropy rises and then becomes constant and saturates to a thermal value. So you can ascribe a temperature to this entanglement value, saturation value.
What is
CFT is, sorry. So you're tuning a theory to a critical point. Okay, so CFT is a point in the flow of couplings where essentially you have scale invariance. So where where the coupling constants don't basically essentially doesn't see any scale. So there is conformal invariance. C stands for conformal. Okay, so there is, and for 2 dimension there is some enhancement of symmetry which allows you to do some calculations. So in some essence you can think of all quantum field theories built out of CFTs, and you perturb away from the conformal points, fixed points, using some relevant operators. Okay, and CFTs are essential to understand phase transitions because they appear when you have continuous phase transitions.
G was taken as a constant throughout. So why is it that only at GC you say there is no scale invariance?
Yeah, so there may be different critical values of a coupling. So in this case, say it's at 0. Okay, so G was some non-zero constant till time t equal to 0, and suddenly it was tuned to 0. So suddenly we quench the system to a gapless point, to a critical point. Okay. Okay.
Why do you get scale invariance at the critical?
Is that the question? Okay, so at the critical point, if you look at, so basically all the couplings are functions of the scale in general, because if you calculate any observable, you will see that there are divergences, and to make sense of those divergences, you have to redefine the coupling. This is called renormalization, right? But at critical points, you will see that the coupling doesn't flow, doesn't depend on the scale. Okay, and that happens that the value of the coupling where it happens is the G critical. In this case, for example, for a massive free scalar field theory, 0 mass is a critical point. So you can think of this as the mass of a scalar field theory, and I'm tuning it to 0. Okay, and the interesting thing is that when you do this, you will see, and if you calculate the entanglement entropy of the system, you will see that that entanglement entropy rises up and then saturates to some constant, some thermal value, and it saturates to a value to a thermal value whose temperature, and you can figure out. So for example, so these are different. So the different colors here indicate these different heights from which I am doing this quench. Okay, so for example, this black line indicates I am doing a quench for a very small value. Okay, the gap is small, whereas this yellow line is a really high quench I am doing, large amplitude quench I am doing. Okay, so for different colors I have different saturation values. Okay, and for each of these colors I can find out what is the corresponding temperature, which describes the entanglement entropy of this saturation value. Okay, it turns out that that temperature which I will get from here is the same temperature which I will get if I match the energies. So if I do this quench and I look at what is the energy generated during the quench and match it to some thermal answer, I can solve this equation for T, temperature. And this temperature is proportional to this gap. Okay, and this temperature enters, for example, in this case, the entanglement. In other observables also, this temperature will start showing up. So this is one way where you have some universal signatures in observables in non-equilibrium. Okay, when you are quenching to this, when you are doing these critical quenches. You can consider even very simple quantum mechanical system, just two oscillators which are coupled. Okay, so there are two oscillators x and y, and they are coupled with a non-integrable term, x square, y square. If it was x, y, you could have separated it out. It would be integrable. But it's x square, y square. And now what you do is you change g from some non-zero value to some other non-zero value. So if you do this change, you will, what will happen is you will pump in some energy. Basically, you are pumping in some energy, right, to the system. You are changing the Hamiltonian explicitly. And then you can ask, you can measure that energy, and you can ask whether that energy can come from some thermal system. You will get some temperature for that. And then you can ask if that temperature shows up in any of your observables. Does your correlators also see that temperature at late time? So these are the kind of questions. Okay, so for example, you can measure the energy. If you measure the energy, you will find that this temperature, not surprisingly, increases with the amplitude of the quench. You solve this equation. So you basically, you calculate, so here N0 is the eigenstate of the Hamiltonian with this value of g, with g naught. And then you are calculating the expectation value of the Hamiltonian with this value of g, g1. So the Hamiltonian with this value of g, this state is not an eigenstate of this Hamiltonian. So that's why it's non-trivial. And you are matching this with a thermal ensemble for this system H1. And you are finding out a temperature, solving for T. This T, of course, depends on how much you are changing G. And the way it is depending is this way, very straightforwardly. You do a larger quench, you see high temperatures. And you can ask whether this temperature shows up in some other place. Okay. Yeah.
What's the graph of the previous slide?
Yes.
What is this graph?
This is how G is changing as a function of time. This is time. Sorry, you can't see from there. So this is time, and this is G. So G is constant till t equal to 0, and then suddenly you ramp it up.
So the system that you are representing Hamiltonian?
Yeah. So after, for positive time, it is evolving with a new Hamiltonian.
And before that, the fixed Hamiltonian about?
Yeah, so both are fixed Hamiltonians. It's fixed here, it's fixed here. Change is happening only at t equal to 0. You can also consider, so it's an interesting question. You can consider smooth changes. It's always changing, it's linear in time, G.
For positive time, the original Hamiltonian is switched off.
So the Hamiltonian itself is changing. So now the Hamiltonian is just the Hamiltonian with this G. So you can think of the Hamiltonian with a theta function with this G. So original Hamiltonian, there is a G which is non-zero, 1, yeah. But you can consider different setups. You can consider different profiles of G also.
This is a non-perturbative problem in the sense that your states suddenly
Yeah.
exchange
Yeah.
one instant of time.
Yes.
You can't start from the states for the lowest coupling and get
No, absolutely no. Yeah.
Only information that comes is in the next slide you have.
Yes.
Hamiltonian, there this N naught is the states for G naught.
N naught is the state for G naught. And then, so N naught is a state for G naught. So this N naught will appear as a very highly excited state for the for the Hamiltonian with G1. So it's not perturbative in that way. Yes.
Motivation behind taking this Hamiltonian, this kind of.
Oh, this Hamiltonian. Okay. So so you can motivate this kind of Hamiltonian in many ways. So one is so this is one of the simplest two-body non-integrable Hamiltonian, one of the simplest non-integrable Hamiltonians, which shows also in the classical limit. We'll come back to this Hamiltonian. It shows also classical chaos. Okay, and we will see that in some aspects of quantum chaos, semi-classical chaos I should say, also this temperature will appear. Okay, that is one way because it is tractable. Another thing is that this is what you get also if you compactify gauge theory. So I will not go into that, but there are people have studied this in context of also compactified Young mills. If it was integrable, then you will see the energy will keep oscillating. So you try out that. But okay, so we are talking about this value, right? This average value at late time of some observable. But we should also talk about the fluctuations about this average value. Right? It's no good describing an average if that average is not, if it's not a true average, right? If there are large variances. Right, so we should look into the suppression of the variance also. So you can try to compute what is this variance, and you will find out very simply. You can compute this. You will find out that this variance is proportional to the mod square of the off-diagonal matrix elements in the energy eigenbasis. Okay, of some operator. So say you are measuring some operator A as a function of time, and you look at this difference, this variance from this mean value, and you do this time average of that variance, you will find out that this is proportional to the mod square of this off-diagonal matrix element. Okay, and then this sum you can write as an integral, where density of state you write as e powered entropy, right? So then you see that this needs to be small. So when can this be small? This can be small when these off-diagonal elements are suppressed at least like e power s minus s, right? Only then, because this can be a huge factor, e power s. If there are many states, this can be a huge factor. So this can kill off that term, right? If this goes like, if a alpha beta goes like e power minus s by 2 for alpha not equal to beta, then it can kill this term. Right? Then there is a chance of the variance being small. Okay, so that motivates the eigenstate thermalization hypothesis, which is a statement about these off-diagonal terms in the energy basis. Okay, you look at this in the energy basis, and there is a diagonal piece, but the main statement is about this off-diagonal basis. Okay, there is this suppression. The main statement is about the suppression, e power minus s by 2. And this is this is a plot from some non-integrable model. You look at some observable between eigenstates, and this bright line indicates that most of the support of this matrix comes from the diagonal. So this is taken from some review, from this review. So you are encouraged to look into this for many examples, where you can explore this hypothesis. Okay, so this is what motivates this, and you can ask this question also in quantum theories, whether quantum theories which we were looking at, these critical quenches or this other quenches, whether they respect this ETH. So this eigenstate thermalization hypothesis, or the ETH for short.
So we are finding the fluctuation, but this is a equation for the mean, since mean that A.
No, so we saw that in the fluctuation, this is what enters. That is why we are looking at this. Yes, and this is also not mean because these are off diagonal, alpha not equal to beta. Yeah, but good. Yeah, so this is important. Okay. So then one thing people realized is that this is related very deeply to the problem of conformal bootstrap. So conformal bootstrap is a program which was originally started by Polyakov. And then later on resurrected in these papers due to some numerical achievements, where you try to map out space of all possible CFTs, which are building blocks of quantum field theories. So like you have a fixed points are these critical points where the coupling is not flowing. You have a UV fixed point and a IR fixed point, and deformations of this fixed point can take you. If it's a relevant deformation with respect to this point, it can take you to this point. Starting from CFTs, you can in principle explore different theories, different possible theories. So it's important to realize what are the consistent CFTs that you have. Okay, that is the grand goal which Bootstrap tries to achieve. Basically tries to impose some non-perturbative constants on the data of a CFT. So what it means by data? By data, it means that if you have some list of numbers, which is this data, then you can compute any observable in that CFT. And it consists of some list. It consists of the spectrum, which is a list of scaling dimensions, which tells you basically that if you look at correlation functions at the fixed point, how they scale if you scale your space. And anomaly coefficients, so the scaling which is classical symmetry may be anomalous. So for something called a central charge, which is a measure of the degrees of freedom that appears as a data. And importantly, what appears also as a data are operator product expansion coefficients. So these are when you take two operators and you fuse them. If it's a field theory, if it's a CFT, you get another. You can write that. If you look at two operators from very far away, you can think of that as sum of local operators, just one operator. And the coefficients that appear in that decomposition are operator product expansions. So in terms of OPE coefficients, the spectrum, data of the spectrum and the anomaly coefficients, you can write down any correlation function, any observable in a CFT. So this is the data. Okay, and the Bootstrap program tries to find consistent data. So given a data, given a list of this spectrum, anomaly coefficients and OPE coefficients, the Bootstrap program will tell you whether it's a consistent CFT or not by using things like crossing symmetry, unitarity, the things that you demand out of a theory. Okay, the symmetries of the fixed point. And there is something else which the CFT is endowed with, is operator state correspondence, where the operator acting, a primary operator more precisely, acting on the vacuum is same as a state indexed by that same operator. Okay, and these are precisely these OPE coefficients, which appear as in these 3-point functions. So this is a data. So what I am saying is this O1, O2, O3, this 3-point function is part of the data of any CFT. And this state, if it's a primary, this state is a energy eigenstate. Okay, if it's a primary operator, it's an energy eigenstate of the CFT Hamiltonian, which means that this properties of this is same as properties of this kind of matrix element. So this brings Bootstrap, this builds the connection to Bootstrap. The statement of ETH is also a statement on OPE coefficients. And so I just told you that there is a way to constrain this data. So of course, what you will do when you realize that there is such a connection, you will try to see if the constant that you get on the OPE coefficient, whether it respects ETH. So that you can do, and in 2 dimensions you can do it. You have some other extra symmetries to play with, modular symmetries, and you can do it, and you can basically look at a 2-point function in high temperature. So for a 2D CFT, in the Euclidean version, you can think of high temperature theory on a circle as being on a torus, because time is also periodic, right, in a thermal theory, Euclidean theory. And this you write a decomposition and the OPE coefficients appear. Basically what happens is you have these 2 external operators, and you can write it as fusion of 2 operators which run through the torus. So you sum over this I and j labels. And what appears here and here are 3-point functions. Precisely those 3-point functions which we are after. And these, the high energy, so these are some functions which depend on the dimensions, the temperature, and so on. So these are functions which are known. Okay, in high energy these are known, and the high temperature behavior of the entire correlator is also known. So both these sides are known, and you want to extract out this piece. So you see, you have to just do an inverse Laplace and an inverse Fourier transform to get this piece out. And you can do that. You can do that, and you will find, at least means asymptotically for very high energies, you will see that there is this entropic suppression. So it is consistent for these large energy states, that these are they respect ETH. Okay, so this is definitely a universal data of a CFT. Okay, and it connects to this thing that we demand for thermalization. Okay, so this off-diagonal. So of course, when I am talking about constraints on off-diagonal matrix elements, off-diagonal matrix elements, of course, play important role in dynamics. And extremity of dynamics is chaos. And furthermore, you expect a chaotic system to be more thermal. So you can ask whether these effective thermal descriptions, whether they enter into some notions of chaos for quantum systems. So, but chaos is a very classical concept, right? So one easy example to think about chaos is to take two trajectories, free trajectories, but put some non-trivial boundary condition. Separate out these trajectories little bit initially, and then as time progresses, they will become very further, exponentially far apart, right? And the way it depends on sensitively on the initial condition is characterized by something called the Lyapunov exponent. Right, so they are exponentially sensitive to the initial conditions. So this classical notion of chaos. So a classical notion of chaos is therefore measured by how much your trajectory at time t, how it depends on the initial conditions q0. So this you can write in terms of a Poisson bracket of q at t and p operator at 0. Okay, so the natural quantum analog would be to replace this commutator with replace the Poisson bracket with commutators. So now you can try to see how this quantity grows, but this quantity, if you use ETH, if you use things like ETH, you will see that this there are a lot of phase cancellations. This is too simple because this saturates again. The time dependence goes away very quickly. So you consider the next higher order generalization, which is you square the commutator. You square the commutator of two operators at two different times, and you look at that expectation value. You find if it's a chaotic theory, you will find that there will be some regime where this will grow exponentially. Okay, this is called the out of time ordered correlator. This is not the out of time. If you expand this out, there will be a piece which will be A of t, B of 0, A of t, B of 0. It will come from the cross term. So that is the out of time order correlator. That actually has a behavior which goes like constant minus some small parameter e to the power lambda t, which makes this commutator grow with some exponent, the Lyapunov exponent. If you use the inputs like ETH for the matrix elements, for the off-diagonal matrix elements, but you have to use also some ansatz, not just for E alpha, E beta, but also higher moments. You have to use some ansatz. If you use some ansatz motivated from ETH, you will find that this lambda is bounded in a thermal state. If you calculate this is a thermal state, this is bounded by 2 pi times the temperature. Okay, this bound has also been found using analytic properties of the OTOC. Okay, but it can be also derived using ETH like ansatz. Okay, you can see this paper. So then you can ask whether whether this effective temperature that we were finding in non-equilibrium, whether that enters into this lambda via this bound. Because there is a bound in terms of a temperature if you calculate this in a thermal state. And what we are saying is, if we quench the system, we are thermalizing the system, right? At least for some operators, we are thermalizing the system. So that means that for some operators, it behaves as if it is in some thermal state. So whether that same thing applies to Lyapunov index, that's the question. So you can look at the simplest theory again, one of the simple theories again, which is this coupled oscillator, and it has chaos. So these are Poincare sections. With increasing energy, you see it becomes chaotic, more and more chaotic. And classically also there, of course, there is a Lyapunov index, and classically the Lyapunov index goes like energy to the power 1/4. And you can study, you can put this, you can put this Hamiltonian in you can study this OTOC in a thermal state, which is to study this commutator here, this commutator. And you can try to extract out a Lyapunov index. You will see that this commutator again grows exponentially with time. And you can extract out a Lyapunov index, and you will see that that depends on temperature. It goes like T power 1/4. Now what you want to do is, instead of doing it for a thermal state, you want to look at this commutator square during quench. So you do the quench and you calculate this commutator squared and see, and you want to see how this Lyapunov index depends on the amplitude of the quench. Because you remember that amplitude of the quench was related to the temperature, right? The effective temperature. The effective temperature was proportional to the amplitude of the quench. So if everything goes accordingly, then you will expect that this lambda, this lambda will go like delta G to the power 1/4. So and that is what you see also. You find that there is a regime where there is exponential growth of the commutator, and it fits very nicely with delta G to the power 1/4.
This problem you have thermal states that equal to 0.
No, so here, no, this is zero temperature calculation again. So here I have that N0 state, and I am evolving with this new Hamiltonian, and I am calculating the out of time ordered correlator. And I am finding this all again has this has a Lyapunov which grows with the amplitude of the quench.
And the previous slide that you showed,
That was with the thermal. That was with the thermal. Yeah. So same thing actually you can also see in critical quenches. You again see that temperature which appeared in entanglement entropy, for example, and the energy. That again appears in out of time ordered correlator for even for CFTs, for critical quenches. Okay, so these were all everything about sudden quenches. But there are also a lot of universalities associated with smooth quenches. So if you smoothly quench the coupling instead of doing sudden quench. So someone was asking that if you can do smoothly, and especially if you do it through a critical point, no matter how slowly you do it, you will end up breaking adiabaticity because the gap is closing. As soon as the theory is becoming gapless, as soon as you are going critical. So adiabaticity will break down, and then that sets a scale in the system, which is called the Kibel-Zurek scale. And then if you measure any correlator in this regime where adiabaticity has broken down, you will find a scaling with this scale. So this scale of course depends on the rate with which you are doing this change. So you will expect, if you measure any correlator in this region, so this is one experiment done by Sadler and others, where there is a quench done, and with time of quench you see some defects are growing. And if you measure this, the rate of growth of these defects within this regime, you will see that they follow some scaling with the rate with which you are quenching. Okay, and if adiabaticity breaks down at some scale, that scale is set by this rate, and then the statement is correlators are dictated by this scale, this TKZ, this T Kibel-Zurek. So in terms of this delta T, it will go like some power law, if you measure it within this regime. There are this is a universality associated with the rate. There are also universalities associated with the amplitude of the quench, smooth quench.
But then these calculations that you do of O delta,
Yeah.
is that in CST or?
So I will show. So now you can try to verify this in different models. So you can do it in free field theory, for example. So you can change the mass as a function of time. So this, for example, this is, so there is this book called Birrell and Davis, Quantum Field Theory in Curved Spacetime. So there there is a section on studying scalar fields in different time dependent geometries. So in some time dependent geometries, you can think of that as time dependent mass. So there you can find the modes explicitly. And if you can find the modes explicitly, you know how the in vacuum and the out vacuum are related. So you know these Bogoliubov coefficients which relate the in vacuum in terms of the out vacuum. So they are now non-trivial because it's a time dependent theory. So you know the modes. So you can, and what you need to calculate is you are looking at this operator in the in state. So you are looking at this non-trivial operator which has this non-trivial evolution, phi square operator in this in state, and if you use the modes explicitly, you will find that there is particular scaling with the rate of the quench.
So what is in vacuum and out vacuum?
Yeah, in vacuum and out vacuum. So if you solve for the modes, it's a second order differential equation. You will get two solutions, right? In this case, you will get in terms of hypergeometric functions. So in vacuum is defined as that combination which behaves like plane waves with positive energy at far past. And if you take a combination which behaves like plane waves with positive energy at far future, that's out vacuum. So the same mode doesn't become out vacuum. That is the point for time dependent geometry. Does not become. That's why there is particle creation. So the in vacuum is not the out, is not same as the out vacuum. And sorry, sometimes the pointer is. So you can see this kind of scaling. This scaling which Kibel-Zurek predicts, you can see this in this case in free field theories. You can also study theories on the lattice. For example, you can study the Ising model and do a smooth quench, transverse field quantum Ising model, and do a smooth quench of the magnetic field with time. There is a critical point also there. So you will expect Kibel-Zurek scaling, and you also find that Kibel-Zurek scaling. In this case, I am not going into this. But then, going back to your question, can we go beyond free field theories and look at these scalings? So something we can try to do are large N field theories. So where we have control, and it's also non-perturbative. And in some regimes, we can even try to look into perturbative field theories. But perturbative field theories, we will not typically capture these scalings because these are non-perturbative states. But large N field theories, we can do something. So I'll move on to this, but I'll pause if there are some questions for this part of the talk. So main part, yeah. So next slides I will go quickly, where I will talk about Kibel-Zurek scaling in large N field theories. So if there are no more questions, I'll move on. Okay.
So has
Yeah.
there been any study like when you have like these quenches and when you have different parallel coupling, but is it ever happened that one considers like a thermal state for some coupling and see what happens when you use the coupling approach?
Yeah, so there has been some studies like that also. So you start with a thermal state, and those are thermal quenches, And yeah, but those you can study using these same techniques.
But does it guarantee that the
Usually, so this is case by case. So there is no theorem, but usually you find that you just go from one temperature to another temperature.
suppose I have the new quantum field theory of
Yes.
the new Hamilton wave. If that is having some random eigenvalues or random matrix,
Yeah.
so they are necessarily going to thermalize or there is nothing?
So I will expect they will thermalize, but I don't know any theorem. So also thermalization also is as we are seeing, is a operator dependent, observable dependent statement. That if I look at very non-local observables, they may not be thermal even in a very random change where I do, because means of course pure density matrix cannot go to a mixed density matrix unitarily. So but if I am confined with looking at observables within some short distance, those may look thermal.
And there were these initial works by Shetty
Yeah.
mentioned thermalization through chaos.
Yes.
So is there any new updates on it that right now is there any agreement that always the thermalization happens through chaos?
No. So of course random matrix theories fit very well with the ETH ansatz, but now I think one major effort is to go beyond random matrix theory and to see whether in other interacting theories also whether we can have these kind of statements, whether these kind of statements hold at least for some time regimes, and what are those time regimes. So these are the questions mainly. Okay, so the theory we will look at is the gross-Nephew model. So very quickly, so I don't have much time, so maybe I will just I can take 10 minutes. Okay, thanks. So okay, so this is a model with large number of flavors of fermions. These are psi, and these are two-dimensional theory, and as you can see, this is interacting theory. G is non-zero. And this theory is very interesting because it shares many features with QCD. So there is asymptotic. If you calculate the beta function, you can actually integrate out the fermions and look at the beta function of this theory. You will find that it is asymptotically free. Beta function is negative. You will find that there is dimensional transmutation in the sense of there is spontaneous breaking of symmetry. There is a Z2 symmetry in this theory, which takes psi bar psi to minus psi bar psi. There is a Z2 symmetry here, and that gets broken by a non-zero generation of this condensate, this sigma. This is like chiral symmetry breaking in QCD. And there is a cutoff appears here explicitly in this equation. So this is proportional to the cutoff, and it's exponential in the coupling. So only G equal to 0, the UV fixed point, which is the trivial fixed point, that is the symmetric point in this theory. So there is Z2 broken phase in this theory at 0 temperature. But however, you can turn on a temperature and see what is happening in this theory. And at finite temperature, symmetry gets restored. So this sigma becomes 0. So if you look at the effective potential for sigma, at 0 temperature or below the critical temperature, you have these two minimas for sigma, which are these values. And then as temperature rises, it becomes 0 after a critical temperature. So now what we want to do is to quench this G. Okay, and then if we quench this G, we should see even at 0 temperature, by quenching G, we should be able to see that this symmetry is getting restored, because as we are discussing, that quenching is thermalizing the system. Right? If it thermalizes the system, then maybe it can thermalize it enough to restore the symmetry. Okay, clear what the question is? V is the effective potential for sigma. So if you integrate out the fermions, so what you do is, so technically you write this effective action in terms of sigma, and when you write it in terms of sigma, it becomes quadratic in this fermion. So you can integrate out the fermion. So you can sum over all the loops in some way in large N, all the quantum fluctuations of psi, and then you generate a effective potential for this V, and that tells you if there is whether there can be symmetry breaking or not. Okay, and then so there is a technique to study this. I will not go into this, the non-equilibrium model using the Schwinger-Keldysh framework, and this large N allows us to solve these time dependent problems in Schwinger-Keldysh. So but the problem, the statement of the problem is, I will make this G time dependent, I will quench this G, smoothly I will quench this G, and see what is happening to this sigma. So if it was for a fixed G, this sigma at 0 temperature is non-zero. I want to see whether it becomes 0. So I will go to the results. So this is, I am changing G. So if I am changing G from some value to some other value, so this orange line corresponds to the value of sigma corresponding to this G. This green line corresponds to the value of sigma corresponding to this G. And if I do it very slowly, or do a very small amplitude quench, I will see that sigma goes from one value to the other value. It is tracking, okay, adiabatically. So symmetry always remains broken. However, if I increase this quench amplitude beyond a certain scale, okay, beyond a certain scale, if I increase, then it starts to follow and then suddenly it turns over. Okay, so this delta T2 is smaller, which means the rate is faster. I am doing it faster. If I am doing it faster, then it turns over. It turns over and it goes to 0, it restores symmetry. That means if I am doing it faster, I am heating up the system enough that I am restoring the symmetry. It starts to follow and then there is a sudden change of tendency to follow. And actually you can make it more quantitative in terms of temperature. You can extract effective temperature from this gap by comparing with the thermal gap equation. You can extract a temperature and you find, so you see, if you can see the colors, the two lines which follow are red and green, and two lines which deviate are blue and orange. For the red and green, if you look at the temperature, effective temperature, that effective temperature stays away from the critical temperature. For the blue and orange, they cross the critical temperature. So there is an effective temperature you can extract, and you can also see that those quenches which exceed that, it becomes too fast, those are crossing the critical temperature. Those are thermalizing the system. That's why you are restoring symmetry for those cases. So in principle, using quenches, you can map out the entire phase diagram, because you can figure out how fast you need to go to restore symmetry. You can just look at the condensate, and then you can estimate a critical temperature, and that way you can map out the equilibrium phase diagram using dynamics in some cases. Also, this time where this happens, the time of symmetry restoration, that shows a scaling. So I am not going into it. It actually, one can understand that as a Kibble-Zurek scaling, where it restores the symmetry, at what time it restores the symmetry. That depends on how fast I am doing the quench. Yes.
How does the slow or fast determine what scale determines the slow or fast?
Yeah, that is determined by the initial mass gap. So if it's slow compared to the initial mass gap, of course it has to be slow compared to the cutoff. If it is in between cutoff and the mass gap, that's a fast scaling regime. That we are not accessing here. We are always slow compared to the mass gap. Yes.
So then, if the system is getting
because you know that at finite temperature symmetry is restored in this model.
So this is the feature of this model.
Yes, this model. Usually most models that if it's a local symmetry, order parameter is there, then it restores symmetry. Recently people have discussed some models where there is a entire family of fixed points. Their symmetry can even break at finite temperature, but those are exceptional models. Generally symmetry gets restored at finite temperature as you pump in energy.
Because I'm expecting, because if the system is thermalizing,
Yeah.
you can think of its becoming more chaotic.
Yeah.
You can think of its like symmetry breaking.
No, no, it's the other way around. Symmetry is broken usually by low energy states, by the ground state. Excited states are usually symmetric. So disordered states are more symmetric. So same physics also arises in some other models. Okay, and you can also extend it when there is a more complicated phase diagram. If there is also a U1 charge involved. Okay, then this model has also a chemical potential, and in this case the phase diagram is more complicated. You can try to map out this phase diagram using quenches. So this is not yet successful, but in principle this can be done. So this blue region has been done. So because one can only do this perturbatively in mu. So it's just technical difficulty, but in principle this can be done. This is more interesting because there are first order transitions in this case. Okay, so I am almost at the end of the talk. Now I will not go into in perturbatively. Okay, just one point. Perturbatively, you can look at you cannot look at into these phenomena, but you can look at how renormalization changes. Because now, because of time dependence, you will have to introduce new kinds of counter terms, which will be dependent on time. So if you look at composite operators, you will see that composite operators will have some memory kernel-like effects, which depend on where you have quenched. Okay, so you have to redo renormalization in some way. Okay, so I'll skip this. So conclusion, just to conclude. So an effective thermal description is useful. That is what we have seen in certain dynamical situations. For example, it will allow us to understand even the Lyapunov index in some cases. Thermalization can impose constraints on the possible consistent data in a chaotic theory. Prime example being this ETH connection with the bootstrap. Large N theories are a useful test bed. So large N theories we could explore more, right? Because the analytic tools are available to us. But it will be important to understand the 1/n corrections in non-equilibrium. So that's an open direction. And of course, in principle, one can explore these in generalized Gibbs ensembles when there are more conserved quantities, not just the energy. If there are more things which are conserved, then it will equilibrate to that kind of an ensemble. And how it does that, and what are the universalities associated with that, that's also open. Okay, so I'll end here. Thank you.
Thanks, Diptarka, for this very interesting talk. So questions?
So when you were changing the parameter, then what was exactly the statement? What is exactly the statement of the Kibble-Zurek scaling?
Yeah, so the exact statement is, so Kibble-Zurek arises when you are near a critical point.
Yeah.
Because you have to break adiabaticity to see Kibble-Zurek scaling.
Right.
If you break adiabaticity, there will be a scale where you are breaking adiabaticity. So the Kibble-Zurek statement is that scale where you break adiabaticity, if you now measure correlation functions within this regime where adiabaticity is broken, gets dictated by that scale. So it's that scale raised to the scaling dimension of the operator which you are measuring.
I see.
So if it's not a conformal invariant point, but there is some dynamical critical exponent, that will also appear in the exponents.
Okay, so this is like a universal behavior when you have like smooth parameter change.
When you have smooth parameter change, as a function of the rate of the that you are doing. But you have to break adiabaticity, that is important.
Yeah, adiabaticity is working.
Yeah.
Okay, fine, thanks.
Oh, so I wanted to ask about the OTOC that you showed for the two-dimensional coupled oscillator.
Yes, yes.
So there you said that initially it shows some kind of exponential growth.
Yeah.
But you use this shaded region to like
Extract the
quantify that,
Lyapunov index,
extract
because
the
after
Lyapunov.
that it is saturating. So it's more like a transient chaos which is happening here.
But somewhere I read like usually in such systems, even though they are classically chaotic, when we are calculating
Yeah.
OTOCs, the time is not of the order of the inverse of Lyapunov exponent, so we can't like.
That is true. That's
really
why.
assign
That's
this.
why. Yeah, because these are like objects with very small local Hilbert space size, right? I mean, that's why you don't expect. In large N theories, you have a large scrambling region, so that's why it will be interesting to carry out this OTOC calculation under quench in large N theories.
Yeah.
It will be really. That will be a good thing to try to do.
Yeah. So also like this is a general question. I have not been able to like precisely define quantum chaos like people usually say.
Yeah, there are many notions of quantum
So
chaos.
there are
There is
some
no
notions like
particular
this is one.
definition.
So
I think for me also.
do you have like comments of your own, like is there any universal feature you can see in a system, in a quantum system, some definition of quantum chaos which is universal across systems?
No,
Have you-
it just depends, I think, on what observables you are looking at. If you are looking at some observables, if you're doing measurements, and you can define chaos, how much your late time measurements are sensitive to the initial time measurement. That will be a good enough definition of chaos.
This is one example, but even OTS is one of the
Yeah.
examples. But even in this, for many systems, they show like
Yeah.
a little bit different behavior.
That is true.
than each other.
Yeah, there is no universal. There are some conjectures like the BGS you may be knowing BGS
Yeah,
conjecture.
okay.
Like if the level statistics behave in some way, you expect some kind of a random matrix like behavior.
Yeah, but
But
no
there, I don't
consensus.
think there are
Yeah.
any. Means at least I don't know. Yeah.
because like I was thinking of relating this to thermalization.
Yeah.
So in classical system, if it's chaotic, it is ergodic and it thermalizes.
Yeah.
But
There is no quantum I
but
don't know
like,
if what is
but-
the status of a quantum ergodic theory.
Yeah. So here, like
Yeah,
this
I
is-
don't know. Ajit may know.
Yeah.
Yeah.
So that's why it is much more difficult, I think, in quantum systems to
Yeah.
assign some property that will be satisfied if
Absolutely,
it has
yeah.
to be thermal.
But still we see that sometimes some notions are useful
Yeah.
to explain some observables.
Yeah.
That kind of
Yeah.
things we can say.
Yeah.
That's all.
Thank you.
Thanks.
Quick follow-up.
Yeah.
When you say semi-classical chaos, what exactly do you mean by semi-classical?
Semi-classical, I mean the intuition is coming from this Poisson bracket. That's why I'm saying semi-classical.
Any more questions? Okay.
It is essential that it should be canonical conjugate A and B is
No, not necessarily. You can take the same operator also. No, you can get same operator as same operator at different time can look very complicated. Because if you calculate A of t, it involves in Heisenberg picture, it involves lot of nested commutators with the Hamiltonian. So the operator can grow and become complicated. It can involve conjugate operators. So A of t is not just made out of A of 0. It may be made of other things.
Here it is chosen for simplicity.
So semi-classically, this is what del q t del q0 is p of 0. But yeah, quantum mechanically it can be same operator also.
Okay, I There were already many questions, so we can continue our discussions at tea and snacks outside. Thank you, Diptarka.
Thank you for the questions. Thank you.